Hello, Math 126 students. Going to talk about page 2 of my Spring 25 exam 2. This was the page that was about 14.7, which was how we use partial derivatives. I had promised there would be a question about local max and min, so I hope when you turn to this page, you immediately knew you needed to find the critical points, which meant you had to do the partial derivatives. So you had xy minus 2x, and you had 1/2 x squared minus y plus 1. And you were trying to find when those were both equal to 0. Now, I tried to talk a lot in class about the strategy for solving a system of equations. Again, that's not really a calculus skill, but it's something I gave you a very clear path to. So I commented on how you pick whichever one looks simpler, and you always try to factor first. So you get x, y minus 2 equals 0, and that leads to two possibilities. Either x equals 0 or y equals 2. And there's still this misconception that I tried to dispel, but seemed to have failed for a few. We had most students get this right. 282 out of 460 got this completely right. But the people that got it wrong often were missing points. Our grader was very lenient on this, or had extra points. So as I flipped through, I saw quite a few people that really only lost a couple points, but I didn't change it, but I thought, oh, they could have lost more because we shouldn't be missing a point. If you're someone that made a mistake on your partial derivatives, then something to add to your final exam preparation is to immediately do all the second partials, because you're going to need to do it anyways. So if you made a mistake in your partial derivatives, then add this to your routine where you compute the mixed partials. I mentioned this in class, but actually look at them separately. So do x and then y, which gives x. Do y and then x, which gives x. If those two are the same, that gives you confidence that you probably did your first partials correct. Okay. So from here, these are completely separate. This does not mean you put 0 and 2 together. People are still making this mistake. You don't even start to think about critical points until you've substituted one fact into the other. And we haven't done that yet. So now I'm going to consider if x is 0, that's one way we can make the first equation 0. And we plug that into the second equation, what do I get? This is the same thing I said in class, but maybe now it really hits home. So when you get to the end of this tree here, you're going to put together x is 0 and y is 1. You're not going to mix the two together. There's a particular problem on the homework that people say, well, we did it in one homework. But even in that homework, you can think of it as the structure. The reason you were mixing is because one did not affect the other. And so when you had x equals 0, you had every possible way. But I explained that several times and posted about that. But, some people don't always get the message. Okay, so 2, you plug in 2 for y. And so you get 1/2 x squared minus 2 plus 1 is 0. And that gives me 1/2 x squared ends up being 1. And you get x squared is 2. And so you get two possibilities. X is plus or minus the square root of 2. And now we can put these together. So that gives me two more critical points because there's y equals 2 with this and y equals 2 with this. So there shouldn't be any ambiguity about the number of critical points. If you're still having a problem with that, or you feel like you have to randomly add in extra points or randomly put things together, then you're missing the structure of how we approach the problems. The rest of it was plugging in to the second derivatives and computing d and making the appropriate conclusions. But from what I saw, like I said, the 282 students got it completely correct. The people that got it wrong were missing a critical point. So the main error I saw was an error in this logic in some way. Okay, you can check my solutions for other points. I did want to show you a picture. This is valuable in that I'm studying some multivariable function. There are 3 places where the slope is 0 in both directions. Those are the 3. If I take the tangent plane and go to one of those points, the slope is going to be 0 both ways. So let me plug in one of those points. How about 0, 1? So here's the tangent plane at 0, 1. And you can see it's a maximum. In all directions, it's concave down. If you go to one of those other points, so let's go over to, I don't know, square root of 2 and 2. You get, well, actually that touches both of them. You get a saddle point. You can see that the tangent plane is crossing there, meaning it's concave up in some directions, concave down in others. Very useful that we can find those. Okay, so again, most people got that. Usually you have to do things like that again on the final. So hopefully this gave you a few tips so when you see this again, you can check. No one should ever include points that don't work, meaning on the final, you should take these points and chest them out back here. If you're someone that gave points that don't make sense, meaning that don't make both of these 0, then build that into your routine. Okay. The other problem, what I had promised in class, was that the other problem would either be a short global max and min, or one of the applied max and min from the homework. And I went back and looked at my review because more people missed this than I expected. And so I went back and looked at my review to make sure what I said. And I did say, and this is not meant to criticize, just I wanted to see where my miscommunication was. So I said that if I give an applied max, it'll be one of the homework questions, and the homework questions were minimize distance, minimize surface area or cost, or maximize volume. So I said, make sure you're ready for those things. Then the other thing I emphasized was know the first step. What are we minimizing? We're minimizing distance. I actually pulled this directly from the homework. This was the homework wording. I thought I just changed the function to something else where the same sort of thing happens. So the piece that I'm worried about is the ones where we had no idea how to start. The only thing we should be taking the derivative of is distance. So you'll notice, as I talked about in class, the thing we're minimizing is distance. The first thing I write is distance. What distance are we minimizing? We're minimizing the distance from points on this surface to 8, 2. So the people that lost big chunks of points seem to not know that first step. And it's hard to give much partial credit there. And so my only takeaway is when I say something in lecture about be ready for this, you do have to be ready. I know that I said global max and min or one of these 3 applied max. Don't try to guess at it, I guess, is what I want to say here. Okay, the only thing you're going to be taking so I saw quite a few people make kind of the standard mistake, which is they took derivatives of this, and it's just hard to give really any credit because that's not in the right direction. The only thing we're going to take derivatives of is distance. How do I know that? Because we're talking about closest, we're talking about minimum distance. But I can't take derivatives yet until I make this a 2-variable function. In fact, the question doesn't make any sense yet until we have a constraint in there. What's the constraint? The constraint is that these x, y, and z's have to come from here. And just like we did in the homework, the easiest way to do that would be to get z squared by itself. I did see mistakes in solving for z squared. Now in my head, what I would do is I would add the z squared, and then I would add the 1. So it would be 1 plus 3x squared. So that was a small mistake, but the big mistake was taking derivatives of this. Again, this is the guiding principle, is only take derivatives of the thing you're optimizing. Like, I don't mean this negative, this is sort of hitting this key point. And this works out just like the homework question did, where you get the square root. So it's actually a pretty short question that seemed to hit half the class by surprise, and I did not mean that. Okay, so then the rest of the question is taking the derivatives and setting 0, and that was what that hint was about. The way I like to do this, and the way I mentioned in class, was the derivative of a square root is 1 over 2 times the square root. That's not going to matter in solving this. So 1 over 2 times the square root. In fact, when I mentioned this in class on the discussion board, I just said, you can label this mess for this mess. The reason we don't care, as you saw in the homework, was you are ultimately going to set this equal to 0, and that denominator doesn't matter for doing that. You'll multiply both sides. So you really just had to solve this and this. So there is a bit of a common theme I've seen in recent years that if I ask a question just like the homework, it's often the hardest question, which is a little counterintuitive to me. So that's interesting. Maybe somebody would be willing to talk to me about in office hours, so that I can try to prevent that in the future. Okay, so then you were solving these two things. One of them gave you x is 2. One of them gave you y is 1. Some people made a small mistake at the end. They didn't know what to do to find these 2 points that you're getting. But that's like the homework. Same thing happened in the homework. So you plug a 2 here, you plug a 1 here, you get z squared is 14, and that's where the two things are coming from. And the visual is the same as the homework visual that I posted on the discussion board. So here's the hyperbolate of 2 sheets. There is our point, the red dot, which is the 0.820. And here's what happens if I move the other point around. So none of those are the minimum distance. You see there's symmetry, so that's why there's going to be a point on top and bottom. But the minimum happens when x is 2 and y is 1. It's that point. That's closest. It doesn't look right here because I didn't make it square. If I make it square, you can see it better. There. The function we got, the distance function, is a totally separate function. It's this function. And the minimum of that function happens right above where this is. But the actual question is, where are we closest? So we had to construct this other function that represented the distance. Okay, so maybe trickier, but I wasn't trying to be tricky. I was trying to ask a question just like the homework. So a few people lost a chunk there. And like I said, it's hard to give. I can't really give partial credit for taking the derivatives of this because that's the wrong idea. But it's one question. All right. Hope that explains a couple key ideas.